Yeah, good morning, my dear students. Today we are going to discuss the topic on various interferences in atomic absorption spectrometry. What do you mean by the term interference? Interference is defined as any effect that changes the signal while the sample concentration remains unchanged. So, your sample concentration remains unchanged, but it will affect the final signal as such. It may be physical interference or it may be a chemical interference, whatever it may be. What is the role of this interference in atomic absorption spectrometry? Because the major role is that it causes either the positive or negative error in quantitative analysis. So this is one of the very important, because most of the atomic absorption spectrometry responsible for finding out the concentration of unknown species. So in that case, any elements if you want to identify, definitely this positive and negative error will be more and more in the quantitative analysis if you are not correcting these interferences properly. So I hope it is clear. So how these interferences can be corrected? They can be corrected by counteracting the source of interference or by preparing the standards that show the same interference. So you have to prepare the standards which is matching with the same interference. Either you can do that, or you can prepare, or you can just counteracting from the source of interference. What may be the source and how will you rectify that? What are all the various types of interferences we are using in atomic absorption spectrometry? There are two types of interferences are there in atomic absorption spectrometer. Whenever you conduct any atomic absorption spectrometer experiment, either flame atomizer or graphite furnace, we face two types of interferences. One is called spectral interference and the other one is called non-spectral interference. So non-spectral interference again can be classified into four different types. One is the chemical interference. Another one is the ionization interference. The third one is the matrix interference, which is also called the solvent error or solvent effect. And the fourth one is non-spectral interferences in graphite furnace atomic absorption spectrometer, which is a special case we are going to discuss, right? Now coming to spectral interference, what do you know about spectral interference? Basically, when I talk about the spectral interference, the resonance absorption lines of various elements are narrow, that is around 0.02 nanometer. That is 0.002 nanometer. So direct overlap of between these absorption lines is very rare, right? So unwanted, we can say that the spectral interference is mostly taking place in atomic emission spectrometry or flame photometry, whereas spectral interference will be somewhat less in case of atomic absorption spectrometry. But still we can discuss that. Spectral interference is producing unwanted signals, just an overlap of analyzed signal due to other elements or molecules in the sample, or with the signals due to flame or furnace. Either due to some other interfering elements, you may get some spectral interference, or that is very rare, or mainly due to signals in the sample in the flame or the furnace is one of the reason where you may get some minor spectral interference. So example, the elements that form the very stable diatomic oxides, only those elements will cause spectral interference very often. Example is yttrium oxide, right? They are incompletely atomized at the temperature of either the flame or the furnace. Okay, substances like yttrium oxide are incompletely atomized at the temperature of the flame or furnace. So what is the remedy to avoid the spectral interference, or what is the rectification we are processing for spectral interference? The first important remedy is interferences from the flame can be subtracted by using different background absorption techniques or correction methods such as deuterium arc method, Smith-Hayebji method and Zeeman background correction. So this is deuterium arc method is basically you keeping the lamp and find out the correction, and the other one is Smith-Hayebji method is basically based on the application of electric field we are correcting the interferences, and Zeeman background correction is mainly due to the presence of magnetic field we can correct the interference in the spectral region, right? So these things we will discuss in a detailed manner in the further classes, particularly when we discuss about the various background correction techniques. Now the second important remedy is the best way to deal with the spectral interference or the overlap between the lines of different elements in the sample is to select another wavelength for analysis. you have to select another wavelength for analysis. Suppose if two elements are there, they will produce some spectral interference. A very simple solution is you select suitable another wavelength for analyzing a particular sample. So these are the two methods to avoid the spectral interference as such, right? The second important interference what we are going to discuss is chemical interference. What is chemical interference? Any other chemical will be there present along with your sample during analysis in the atomic absorption spectrometer, and they will try to cause lot of interference. So it is caused by any other component of sample that decreases the atomization of the sample to some extent. Because of that, what problem we are getting? Atomization will not be proper. Okay, it will decrease the atomization. Because once atomization is decreased, what will happen? You will not get the enough concentration of the sample in the gas phase ground state, and automatically the sample will not be going to the excited state, right? So for example, if I have sulfate and phosphate, they decreases the atomization of calcium. Suppose I want to analyze the calcium as a substance. If sulfate and phosphate is present along with that, they will try to mingle with calcium and form calcium sulfate or calcium phosphate. So that time atomization will not be proper, right? So they will form the non-volatile salts and atomization will be affected. So what is the remedy for preventing this chemical interference? A very important method we are using is releasing agents. We are adding some releasing agents, right? For example, chemicals added to the sample to decrease the chemical interference. Releasing agents are the chemicals which are added to the sample to decrease the chemical interference. A classical example for this reagent is EDTA, ethylene diamine tetraacetic acid, and 8-hydroxyquinoline. Both of them protects the calcium from interference effects of sulfate and phosphate, because they will bind before the sulfate or phosphate binds with the calcium. They will go and bind with the calcium. They have more affinity, EDTA and your 8-hydroxyquinoline. So therefore what will happen? Indirectly they will prevent the binding of calcium with the phosphate or sulfate, right? And there are certain releasing agents called lanthanides, right? These lanthanides, La3+, acts as a releasing agent because it interacts with the phosphate and frees the calcium. These lanthanides are having more affinity to have a binding with the phosphate molecule to make lanthanide phosphate. So what will happen? These lanthanides will try to indirectly act with the phosphate and they will make lanthanide phosphate, so that calcium will not be binded with phosphate. So calcium will be left free and atomization will not be prevented, right? So how much amount of lanthanide should be added as a releasing agent along with the sample? It should be around 2000 ppm of lanthanide, parts per million of lanthanide. And the second important rectification for avoiding the chemical interference is fuel rich flame. Chemical interference you cannot avoid, because definitely some interference will be there along with another chemical present with the sample. The second method is fuel rich flame. Will decrease a certain oxidized analyte species that would otherwise decreases the atomization. So this is also important. Example I am giving: acetylene nitrous oxide flame. So there is no interference of calcium with phosphate. If I use this flame, because it is a fuel rich flame, fuel will be very high. So therefore the flame has sufficient energy to decompose the calcium phosphate molecule. Okay, and they will decompose the calcium phosphate molecule. It will be giving more availability of calcium. It will produce more availability of calcium. So they will be converted into atoms. So this is the mechanism, right? So fuel rich flame is also responsible for preventing the chemical interference. The third method used for preventing or rectify the chemical interference is to match the matrix of the standards and the samples. Of course, it is not much more reliable method, but somehow you can match the matrix of the standards and the samples. What type of matrix is nothing but any other material other than the sample present in the container, right? And the fourth method for rectification of chemical interference is use of method of standard addition calibration technique. Method of standard addition, we call it as MSA technique. So this MSA calibration technique is a very widely useful technique, which is also called standard addition technique, and this will be used for quantitative analysis. We will discuss this in a detailed manner when we discuss about the applications of atomic absorption spectrometry, right? So this is also one of the important method to prevent or avoid the chemical interference. Now coming to the next type of interference is ionization interference. So when we talk about ionization interference, basically the molecule present in the gas form will be converted into ions and releasing the electrons. When this is possible, the ionization of the sample atoms decreases the concentration of neutral atoms. See, basically if more and more ionization takes place, what will happen? The neutral atom concentration in the gas phase ground state will be available, will be very, very less. Okay, this is vice versa. If you have more concentration of atoms, ions will be less, and if ions will be more and more, definitely the concentration of free atom will be less in the gas phase. Obviously, it will affect the atomization of the sample. So, example, alkali metals. The alkali metals like sodium, potassium, they have the lowest ionization energy and they are extensively ionized in the flame, and therefore they decreases the atomization of the sample. So particularly for these particular samples, atomization will be decreased, right? Because they have the lowest ionization potential. So how to prevent or rectify this ionization interference? You cannot avoid them. How will you rectify that? You have to add some ionization suppressing agent, or sometimes we call it as ionization buffering agent. Okay. With the sample, you have to add some ionization suppressing agent or ionization buffering agent. So they are extensively, when we use this one, I will just give an example here. In the analysis of potassium, if I want to analyze the concentration of potassium present in the sample, I just add 1000 parts per million of cesium chloride. Because when I add this thing, what will happen? The cesium will go for ionization very fastly compared with the potassium. So when the cesium is ionized, I will get cesium ion plus more number of electrons. And when you have more concentration of electrons, they will suppress the ionization of your potassium, particularly in the sample. Is it clear? This is how the ionization suppressor acts here to prevent the ionization interference. Not only this cesium chloride we are using, we can use any other substance. For example, in the analysis of sodium, we are using 1000 ppm of potassium chloride. So potassium, what they will do? Before sodium will get ionized, potassium will extensively ionize in the flame. So what will happen? Once it is ionized, it will produce more electrons also, and that concentration of electrons will prevent the suppression of ionization of your sodium ions. So like that we can use certain elements like cesium, potassium, rubidium, these type of compounds in a particular concentration of 1000 ppm we are using as a reagent or as a suppressant, and then we are just to suppress this ionization interference, we are adding along with the sample, right? There is another method we are also using to prevent the ionization interference, that is the use of the low temperature flame. When you use the low temperature flame, because see, there are two possibilities for ionization. One is the elements having lowest ionization potential, they will go for ionization. And in the high temperature flame also, they will go for ionization easily. So when you keep the temperature of the flame in a low manner, automatically ionization will be prevented. So these are the two important remedy for preventing the ionization interference, right? Low temperature flame is acetylene air flame. It's a classical example, right? The fourth method, what we are going to see the chemical interference, other than the chemical interference, is matrix interference. So what is this matrix interference? Matrix is something that is present in the sample other than the sample. Okay, whatever is present in the sample which is excluding the sample is called matrix. Anything present in the sample along with them is called matrix. So this matrix may be your solvent also. Due to solvent also you may get the matrix interference, right? So example, I can give one example for matrix interference. For example, milk. Milk contains main concentration, what we are going to analyze in milk, calcium concentration we are going to analyze. But apart from calcium in the milk, it contains the aqueous phase with suspended fat droplets. So you are having the water molecules, fat droplets, and suspended micelles of proteins and minerals. Even proteins are also present, minerals are also present. So these are all the matrix substances. They will cause interference with the atomization of the calcium present in the milk. Okay. So therefore calcium determination becomes very, very difficult, right? So what is the remedy for this matrix interference? We have to add the matrix modifier. I just told in the previous class also, particularly when you analyze the manganese present in the seawater, seawater contains more interference from sodium ion and chloride ion, right? Rock salt will be there. So they will interfere with the manganese ion. So what we have to do is that we are adding some matrix modifiers such as ammonium nitrate. So what will happen? Ammonium nitrate will combine with the sodium chloride and they will form ammonium nitrate and sodium nitrate. So sodium nitrate is more volatile and the matrix gets more volatile and they will quickly evaporate and go away and they will not interfere with your sample, right? So that is what we have discussed, either making the matrix more volatile or making the sample less volatile to prevent the matrix interference, right? So generally we are using matrix modifier, and generic mixed modifier we are using. For most of the samples we are using a generic mixed modifier of palladium and magnesium nitrate. Palladium and magnesium nitrate, it's a common for most of the elements. We just add minor quantity of this matrix modifier along with the sample to prevent the matrix interference. Also we can use MSA calibration technique here. The same thing what we have used for chemical interference. The same thing we can use it in matrix interference also. Then one more method we are using, compare the slope of external calibration method versus MSA calibration method. What is the meaning of this thing? That means there are different methods for quantitative analysis to find out the concentration. One is called external calibration curve method, which is also called a standard curve method. Right? Another one is called method of standard addition calibration, which is called MSA calibration technique. So when I see the slope of the MSA technique and when I see the slope of the external calibration technique, if both the slopes are parallel to each other, then there is no matrix interference. Suppose if they are not parallel, we can say definitely matrix interference is present. So this is the way we can try to see that if they are parallel, we can say that the matrix interference can be avoided or rectified. Right? And the last one important aspect is that non-spectral interference in the graphite furnace atomic absorption spectrometer. What type of non-spectral interference with the furnace? This is basically in the particular graphite furnace only we are getting this type of problem, right? So what is this problem we are facing? Certain elements will try to react with the graphite and they will try to produce the carbide formation. The carbide is, when they get the carbide formation, definitely the atomization will be a big problem over there, right? So what type of elements? Actually the elements should not react with the graphite, but certain elements will react with the graphite and they make the graphite contains what? Carbon, and these elements will try to form the corresponding carbide. What are those elements? Those elements we should be very cautious. Those elements are tungsten, tantalum, and then boron, niobium and molybdenum. These are the elements which will try to form the corresponding carbide when they react with the graphite in the furnace. Tungsten carbide, right? Boron carbide. These unwanted carbide will be produced. So what these substances are produced, so what will happen? It will affect the atomization of the particular element boron or your tungsten. This is a problem we are facing. How to rectify these things? The only rectification is go for the pyrolytic graphite. Use of pyrolytic graphite. That means a dense layer coating of graphite which will seal the porous layer of the graphite so that your elements will not try to interact or react with your particular graphite and it will not produce the carbide formation. So this is what all about the various types of interferences. One is the spectral interference, another one is the non-spectral interference. In case of non-spectral interference, there are different types. It may be chemical interference, ionization interference, matrix interference, and there is some special non-spectral interference taking place in the graphite furnace atomic absorption spectrometer. Not only these things, even other aspects also there, releasing agents and other things we have discussed. I hope you understand it in a clear manner. So thank you very much, my dear students. Thank you very much.